Hello everyone, I am Suchita Moril. Welcome you all in the video lecture on the topic Mathematical Modeling Mechanical System. Mechanical system mainly divided into two parts: translational mechanical system, rotational mechanical system. The translational mechanical system moves along a straight line and it has three ideal elements: mass, spring, damper, which are given in the diagram. Then rotational mechanical system moves along a fixed axis. It consists of three ideal elements. First is moment of inertia, torsional spring, and third one is damper or dashpot. Now mass. Mass is a property of a body which stores kinetic energy, and this mass is directly uh, proportional to the acceleration. Therefore, by using the law of proportionality, this Fm is directly proportional to A, where A is the acceleration and x is the displacement. Therefore, this equation F equal to m into d2x by dt square, if we write down in the form of velocity, we can write down this as m into dv by dt. Here, mass m, F is the force and x is the displacement. Now spring is the element which stores potential energy, and this force is proportional to the displacement of the spring. Here, therefore, F is directly proportional to x. Therefore, F equal to kx, where k is spring constant, x is the displacement. Here, this is the spring and k is the spring constant. Now, the damper or dashpot. F is applied to a dashpot, then it opposes by the force due to the friction, and this force is directly proportional to the velocity. By using the law of proportionality, here this dv is directly proportional to v, and this f equal to f dx by dt, or we can write down here f dx by dt. It is denoted by damper is denoted by v or small f, where this v or small f is the frictional coefficient, v is the velocity, and x is the displacement. Moment of inertia, as same as translational system, rotational mechanical system is also this moment of inertia stores the kinetic energy, and this kinetic energy is proportional to the acceleration, and therefore we write down this T equal to T means applied torque, and J means moment of inertia is directly proportional to alpha. Alpha means angular acceleration. Therefore, the formula is J into d2 theta by dt square, here where theta is the angular displacement. This is the moment of inertia, torque, and angular displacement along the rotational system. Torsional spring also works as same as translational system. It stores the potential energy, and this torsional spring is applied to spring, then it opposes the torque due to the elasticity of the spring, and this is torque is proportional to angular displacement. Therefore, this T is directly proportional to theta. Therefore, T equal to K theta. K is the torsional spring constant here, and T is the torque. Theta is the angular displacement. Damper or dashpot. Torque is applied on dashpot B, then it is opposes the torque due to the rotational friction of the dashpot. This is torque proportional to angular velocity. This b or small f here. Therefore, T equal to B into d theta by dt or F into d theta by dt, where B or F is the rotational frictional coefficient, omega is the angular velocity, theta is the angular displacement. These are the formulas for them. These ideal elements of mechanical system, that means translational or rotational. Now we derive the differential equations for this. Differential equation of translational system, it is known as mass spring damper system. We consider the mass m attached to a spring and damper on which force Fx, displacement x is positive, actually displacement in this direction, and F, capital F is also works in this direction. Therefore, by and equilibrium position is taken to be zeroth position. Therefore, by Newton's law of motion, we write down here this capital F minus kx, then minus f dx dt equal to m into d2x by dt square. Now we shifted all the terms, these three terms, two terms on the right hand side. Then we get this equation, which is the higher order differential equation with constant coefficient. In this way, we get this equation if we denoted this equation 1. Similarly, we find out the differential equation for rotational system. Here, inertia spring damper system. Consider the rotational mechanical system is consist of rotational disc with inertia J, stiffness K, and the disc rotates a viscous medium with viscous friction coefficient F. This is denoted by small f. Then T is the applied torque. Therefore, by using the equation here, we get T equal to this J d2 theta by dt square plus F d theta by dt plus k theta. This is the equation number 2, and which is the higher order differential equation. In this way, this mathematical model forms the differential equations. Now here variable classifications is mainly in two ways, through variable and across variable. Now here through variable means variable which passes through the element and it has same value at one port and out of at the other. That means, for example, current flowing through the circuit. Current flowing through one point to second point is same. Now a second variable, across variable, a variable which appears across the two terminals of the elements. That means voltage drop across two variables, across the variable, across the resistance, across the capacitors in this way. Now another classification is input variable and output variable. Now through and across variables for ideal mechanical system. These are the very ideal mechanical system, through variable which is denoted by Vt and across variable which is denoted by Va, then integrated through the variables, integrated across variables for translational system and rotational system. Here force, and in your rotational system torque, this translational momentum, angular momentum, velocity difference, which is the across variable, here angular velocity difference. Here integrated, that means here integration of this term is displacement, then we get displacement difference here in rotational, here angular displacement difference, which is denoted by theta. In this way, we write down the through and across variable. This is regarding the mechanical system mathematical modeling. Thank you.